This question talks about four scenarios, A, B, C, and D, where you have this puck and you have this rod, and the puck comes in and it hits the rod at various locations, as well as the rods themselves having a pin. So let's read through there. It says four cases above have four pucks viewed from above, sliding to the right on a smooth table. All right. So first of all, smooth table. What that indicates is that that's no force. There's no force of friction as it's sliding. So that gets to the language of trying to say that there's no outside force acting on it, which is what is necessary in order to have a conservation of momentum. Each puck collides with a stick, and it sticks to the rod. Sticks to the rod. All right, so that's very important. So each one of these, they stick to it, and then it moves with negligible friction. Negligible friction again, as it's rotating with negligible friction. All right, and that's going to be important because what that indicates is that it can rotate with no net torque adding on it. And that's going to be important for conservation of angular momentum. You'll see that here in a second. In all four cases, the pucks are identical, the rods are identical, and the initial velocity of the puck is identical. And then it says that all the pucks are perpendicular to the rod. Okay, so it's trying to tell you that each one of these have very, very similar scenarios. So we're trying to eliminate all the variables. That same pucks, perpendicular to the rod, same rod. The only difference is where it hits on the rod and whether that rod has a frictionless pin or not. All right, so let's get to the question. It says, for each case, determine whether the angular momentum, linear momentum, and kinetic energy are constant. Put a check mark in the box if the quantity is constant, and an X if it changes during the collision. All right, so let's talk about let's talk about kinetic energy first. There should be something in here that should indicate how the kinetic energy changes in this process, and that is that it says that it sticks to the rod. Whenever two objects stick together in a collision, you never conserve kinetic energy. Now, you can conserve mechanical energy, but you do not conserve kinetic energy when the objects stick together. As a matter of fact, when they stick together, you'll actually get some dissipated energy every single time, so I can't even imagine you would conserve mechanical energy either. All right, next let's talk about angular momentum. All right, angular momentum, first of all, with all four of these, you can see that you have a point of rotation at the center, and it says it has negligible friction. So if it's allowed to rotate freely and there's no outside net torque, then angular momentum is going to be conserved in every scenario. Now, what about linear momentum? Is linear momentum conserved? Well, linear momentum says that there has to be no outside net force. Now, we said there's no force of friction. That's good, but you have to take into account that this pin right here, that actually is an outside force when you're talking about the puck and the rod. So if that pin is an outside force, then that means when this puck hits the rod, that momentum will not be conserved. So in case A, linear momentum is not conserved. B, there is no pin, so there's no outside net force, meaning linear momentum is going to be conserved. Same thing with C, linear momentum is going to be conserved, but again in D we have a pin, so therefore the linear momentum is not going to be conserved in this case. Now flipping over to the back of the problem, it says rank the cases according to which one has the most rightward linear momentum instantly after the collision. Okay, so let's talk about the momentum. We're going to go from least to most. So the easiest thing, I think, is to look at which one has the most. Which one has the most rightward momentum. All right, so you see that that B and C both have no outside net force. If both of them have no outside net force, then that means momentum is going to be conserved. So if the momentum is conserved, then that means it doesn't matter where on this rod it hits. As long as there's no outside net force, then B and C are both going to have the most rightward momentum. As far as A and D, let's look at those two cases. A, it hits at the center. And if it hits at the center and sticks to it, then, well, the rod's not going to go anywhere because it's fixed. And if it sticks to it, then the puck is not going to go anywhere either. So both of them are instantly going to stop. That means the least, that's going to have the least because, well, 0 is going to be the least. And then this case D, even though it's kind of a similar scenario in that both of them have the same linear velocity, but it hits not at the center, but at the edge. So once it hits at the edge, it's still going to have some forward motion as it rotates. So with a little bit of forward velocity, there's going to be, for D, is going to have a little bit more rightward momentum. So A is going to be less than D, which is less than B, and B and C are going to be equal to each other because there's no outside net force. All right, now the last part right here, it says which one has the most clockwise angular momentum? Well, if you remember, angular momentum is conserved as long as there's no outside net force. No outside net force. Okay, so, I'm sorry, no outside net torque. No outside net torque. So we have A, when it sticks to it, A is actually going to stop. C, when it sticks to it, it's still actually, they're going to stick together and it's still going to move forward, but there's going to be no rotation because it hits at the center of the rod. So both A and C are both going to have no rotational motion afterwards. All right, now that brings us to B and D. B and D with no outside net torque. Okay, so we have an axis of rotation here. Now that has, that point right there has a negligible friction. So there's going to be no net torque supplied by that pin. Well, this one doesn't even have a pin, but it is going to still conserve angular momentum because there's no outside net torque. So both of these actually conserve angular momentum, which means both of them will have the most clockwise. So both B and D will have the same clockwise angular momentum. And then, of course, those are going to be greater than A and C together.